Welcome to the Carboniferous, where the forests grew in immense, and so did the insects.
Personal space. Most were harmless, but this one seems determined to test that theory.
More than 300 million years ago, long before dinosaurs, Earth entered one of the strangest chapters in the history of life. The Carboniferous lasted nearly 60 million years, so the animals in this journey did not all share the same forest or even the same moment. But together, they reveal a planet of vast wetlands, unfamiliar seas, and evolutionary experiments unlike anything alive today. On the forest floor, danger came armored. One of the most imposing hunters was Pulmonoscorpius, an early Carboniferous scorpion from what is now Scotland. The largest known remains suggest an animal approaching 70 centimeters from claws to stinger far beyond the size of any familiar scorpion today. Its broad pincers could restrain struggling prey, while its curved tail ended in a sting. The exact chemistry of its venom is forever lost, but fossil anatomy indicates that it breathed air through book lungs and lived on land. Exactly what it hunted is uncertain, although smaller arthropods and early four-limbed vertebrates were likely possibilities. The scene may look like a battle between monsters, but these were animals following ordinary instincts, searching, feeding, defending territory, and avoiding injury. Even a giant scorpion could not afford a damaged leg or broken claw. In this dense undergrowth, every vibration in the leaf litter might signal a meal or a larger rival moving closer. The swamp forests were only one face of the Carboniferous. Beyond them stretched warm, shallow seas filled with cartilaginous fishes, bony fishes, crinoids, brachiopods, and reef-building communities unlike those of the modern ocean. One of the period's strangest swimmers was Stethacanthes, a shark-like cartilaginous fish famous for the flat, brush-covered structure rising from the backs of mature males. It has often been compared to an anvil or even an ironing board. Its exact purpose remains uncertain. It may have been used for display, recognition, or close contact during mating. Despite their ancient appearance, these animals were not primitive failures. Sharks and their relatives had already spent tens of millions of years refining replaceable teeth, flexible cartilaginous skeletons, and efficient swimming. Around them moved schools of smaller fish, each occupying its own place within the food web. These bright underwater scenes are a cinematic reconstruction, but the central idea is real. Carboniferous waters supported an extraordinary variety of predators. Some cruised through the open sea. Others entered coastal lagoons, rivers, and freshwater swamps, carrying the shark-like body plan far inland. Where dark rivers entered the forest, another predator waited below the surface. Crassigyrinus was not a crocodile, and it was not a modern salamander. It was a stem tetrapod, part of the broad evolutionary story that produced four-limbed vertebrates, yet its own body was almost completely adapted to water. It could grow to roughly 2 meters long. Its body was streamlined, its limbs were remarkably small, and its skull was broad, reinforced, and packed with sharp teeth. Those reduced limbs were poorly suited for walking. Crassigyrinus instead moved through murky channels with its body and tail, approaching prey where visibility was low. Its large eyes and powerful jaws suggest an aquatic ambush hunter. Fish passing between submerged roots could vanish in a sudden burst of motion. A wide mouth and inward-pointing teeth helped prevent slippery prey from escaping once caught. Creatures like this show that the move from water to land was not a simple one-way march. Early tetrapods explored many lifestyles. Some became increasingly capable on shore. Others remained tied to rivers and swamps or returned to an almost completely aquatic existence. Evolution does not aim toward a destination. It branches whenever a body plan discovers a new way to survive. For much of the Carboniferous, water still shaped the lives of land vertebrates. Amphibian-like animals generally return to wet environments to reproduce. Their eggs and young were vulnerable to drying. That dependence would soon create an opportunity for a very different group of pioneers. Then, the forest floor begins to move. Arthropleura was the largest land-dwelling arthropod presently known. The biggest individuals may have reached about 2.5 meters in length, with a heavily plated body wide enough to make the animal look less like a millipede and more like a moving piece of armor. For generations, its head and diet remained mysteries. Recent fossils of young individuals have revealed short antennae, unusual stalked eyes, and a mixture of traits associated with centipedes and millipedes. Its trunk carried 2 pairs of legs on many body segments, supporting its close connection to the millipede branch. Most evidence now points away from the idea of a gigantic, active predator. Arthropleura was more likely a slow-moving consumer of plant material and decaying vegetation, processing the enormous quantity of litter produced by these forests. High atmospheric oxygen probably helped some Carboniferous arthropods reach exceptional sizes. Many land arthropods deliver oxygen through networks of branching tubes rather than lungs like ours. But oxygen was not the only answer. Food, climate, competition, and ecological opportunity also mattered, and some giant Arthropleura lived before atmospheric oxygen reached its highest levels. Its enormous size was therefore not one simple accident. It was the product of an entire world built differently from our own. Above the forest floor, the air belonged to insects. The giant forms often called Meganeura were griffinflies, ancient relatives of dragonflies, rather than true dragonflies themselves. The largest known members of this broader group reached wingspans close to 70 centimeters. Their 4-vaned wings created a broad, lightweight flying surface, while enormous compound eyes helped track movement through the air. Griffinflies were hunters. They likely intercepted smaller insects in flight, steering with rapid adjustments of their wings and grasping prey with spined legs. They were not built to attack large vertebrates, but an insect of this scale passing close overhead would have been impossible to ignore. Elevated oxygen may have made large insect bodies easier to supply with air, but again, oxygen alone cannot explain everything. Flight style, temperature, prey availability, and the absence of birds and bats all shaped their evolution. The densest parts of a coal forest may have been difficult for the largest species to navigate. Open river channels, clearings, and forest edges could have offered better hunting space. There, a griffinfly could patrol above the vegetation, turn toward a moving target, and accelerate before its prey detected the approach. Beneath those same channels lived another surprise: shark-like predators in freshwater. Xenocanthids and their relatives inhabited carboniferous lakes, rivers, and swamp systems. Many had long, eel-like bodies, distinctive spines near the head, and forked teeth suited to gripping slippery prey. They were not simply modern sharks transported into a swamp. They belonged to ancient branches of cartilaginous fishes that developed their own specialized freshwater forms. Among submerged roots, vision could be limited to only a few meters. A predator might sense movement before it could see the animal creating it. Fish, young tetrapods, and other aquatic prey shared a habitat where the boundary between forest and water disappeared beneath the surface. But the most important Carboniferous animals were not always the largest. On patches of firmer ground, small lizard-shaped vertebrates moved through fallen bark and vegetation. Among the best known is Hylonomus, discovered within the fossil forests of Joggins, Nova Scotia. It remains one of the earliest well-known amniotes represented by body fossils. Hylonomus was not a dinosaur, and it was not a modern lizard. It was a small early member of the great amniote story, the lineage that would eventually divide into the reptile and bird branch, and the synapsid branch that produced mammals. The crucial innovation was reproduction that depended less upon open water. Amniote embryos developed within protective membranes, allowing reproduction to function in drier environments. This did not mean that the first amniotes immediately conquered deserts. It meant they could move farther from ponds and swamp edges than many amphibian-like competitors. Some Hylonomus fossils were discovered inside the remains of hollow, upright trees. The animals may have entered these cavities searching for insects or shelter before becoming trapped, leaving a remarkable snapshot of life upon the forest floor. Small bodies, claws, and reproduction protected from drying would eventually prove more historically important than giant jaws or enormous wings. As the Carboniferous continued, its climate and landscapes changed. Vast wet forests contracted and fragmented across many regions. Drier habitats became increasingly common, separating populations and creating entirely new evolutionary pressures. The giant arthropods did not vanish in a single moment, and amphibian-like predators remained successful. But the balance was shifting. Amniotes could reproduce farther from standing water, explore new habitats, and divide into lineages that would dominate much of the land during later periods. The Carboniferous gave Earth immense coal forests, extraordinary insects, freshwater sharks, aquatic tetrapods, and some of the earliest chapters in the rise of reptiles and mammals. Its strangest giants would eventually disappear, but the evolutionary revolution that began beneath these trees was only getting started. The Carboniferous
Was full of giants, and apparently some of them make excellent transportation.